Thank you very much, Rudra, and good afternoon, everybody. It's a great honor to be asked to deliver this keynote lecture, and I'm particularly delighted that the IEEE meeting on sensors is being held here in India, and I'd like to congratulate both the international team and the Indian team for holding this wonderful meeting over here. I hope all of you, both from within India and outside, have had a great time discussing with each other. And I'll hope you also all have time to visit our institutions and put in place valuable collaborations and extend those which are already there. What I will try to do now is to tell you about two different, apparently disconnected themes where I think sensing the environment is absolutely vital and vital for the safety and sustainability of our planet. And this may be a little broad brush, and that's for two reasons. One, I think it is important to have this broad view. And the second is that I'm no expert in the details of sensors. I would be making a mistake if I were to come and try and talk about that. But I feel that talking about these broad aspects will allow us to see where the opportunities lie for the interface between our environment through technology into feeding back into how decisions about our life and our environment are made. Now, one of the key aspects of discussions which dominate across countries through the entire planet amongst humans is the matter of climate change. Now, there's no question that the Earth's climate has changed substantially over the last 650,000 years. For example, there have been 7 cycles of glacial advances and retreat, and the last ice age ended about 7,000 years ago, marking the beginning of the modern climate era. And this was also the time when human civilization started to grow. Most of these climate changes have been attributed to a very small variations in Earth's orbit, and that changes the amount of solar energy our planet receives. And therefore, climate change is not unusual. It's taken place several times in the history of the planet. So it's reasonable to assume that changes in climate are due to changes in the pattern of Earth's orbit about the sun. But while solar variability has played an important role, what's happened recently in climate change is largely due to human interference. And that's been well documented. And the first part of my talk, I'll try to tell you how sensors have actually resulted in our understanding that this is indeed the case. So given that, and I'll give you some data, given that climate change is a serious problem, and given that much of it is human-induced, what can we, particularly as scientists, do? Now, there are two views here. One, there are people who have an extreme view that it's already too late to do anything. And if one does something now, there's no reason to believe that the rate of reversal will be anything predictable or anything which one can see within a reasonable period of time. There are yet others who think that while things are in bad shape, it is certainly feasible that mitigation as well as other measures can reverse this warming. Now, let's look at the facts now. Why do we think that human-induced climate change is important? What is the evidence for global warming? Now, this graph illustrates the change in global surface temperature relative to a 1951-1980 average temperature, and 16 of the 17 warmest years in the 136 record, all have occurred since 2001, with the exception of 1998. The year 2017, according to NASA, ranks as the warmest on record, 2016. This research is, again, consistent with similar constructions prepared by the Climatic Research Unit and the National Oceanic and Atmospheric Administration of the US. So these data is taken from NASA, and this points to human-induced climate change as being, as temperature changes being very important. Now, carbon dioxide is, again, a very important heat-trapping greenhouse gas, as you all know, and this is released substantially through human activities such as deforestation, burning fossil fuels, as well as natural processes such as respiration and volcanic eruptions. Now, this graph shows that CO2 levels measured at Hawaii at the Mauna Loa Observatory in recent years with an average seasonal cycle has been removed, and that has steadily been going up. Again, another way to measure historical CO2 level changes is by looking at ice cores, and phenomenal sensors have been developed to look at that. And these direct measurements provide evidence that atmospheric CO2 has increased since the Industrial Revolution. And this is the Vostok ice core data from Petit et al., again from the NOAA and the Mauna Loa Hawaii record. Now, Arctic sea level ice is another measure of human-induced climate change. And Arctic sea reaches its minimum each year in about September each year. And this September Arctic sea levels is declining at a rate of 13.3% per decade relative to the 1981 to 2010 average again. And this graph shows that decline since 1979. And this is derived from satellite observations. So the 2012 extent is the lowest in the satellite record. So whether you measure by satellites, whether you measure by ice cores, or whether you measure directly, the changes are dramatic. Now, all these measurements are terrestrial measurements, but this one, the Gravity Recovery and Climate Experiment, GRACE, and that experiment is now ending, there might be a next avatar. GRACE is the first Earth monitoring mission in the history of space flight whose key measurement is not derived from electromagnetic waves either reflected off or emitted or transmitted to the Earth's surface and or the atmosphere. Instead, the mission uses a microwave ranging system to accurately measure the distance between two satellites. And because of changes in gravitational pull, depending on sea level changes or other changes on Earth, these satellites can go slightly up or down, but the microwave measurements will have to be to calibrate to keep the distance absolutely the same, and that can give you a measure of very fine changes. So the ranging system is very sensitive and can detect differences in distance between these two satellites to the level of 10 micrometers. So if you triangulate, you can see very small changes in height on the Earth. So data from NASA's GRACE satellite show that land ice sheets in both the Antarctic and in Greenland, which is the next chart, have been losing mass since 2002. So this is, completely global, the entire planet you can look at, and both ice sheets, this is Greenland, both ice sheets have seen a dramatic decline. Now, sea level rise is caused by two factors related to global warming: the added water due to melting ice sheets and glaciers, and the expansion of seawater as it warms up. The graph now, from looking at coastal tide gauge data, shows how much sea level has changed from 1870 to now. So sea levels are also rising. So you can also track through satellites the changes in sea levels since 1993, and that's shown over here. And finally, you can go and look at greenhouse gases. These are primarily water vapor, carbon dioxide, methane, nitrous oxide, and these are a thermal blanket. And this can look at, this blanket is very valuable for supporting life on Earth. And most climate change scientists agree that the main cause of the current global warming trend is human expansion of the greenhouse effect. And the question is, there are some greenhouse gases such as water vapor, which are in a feedback cycle, so the amounts can be regulated, and others which are not. CO2, for example, has that effect, but nitrous oxide and methane don't. So the consequences of changing the natural atmospheric greenhouse are difficult to predict. And there are many theoreticians and experimentalists working on that. And on the average, Earth will become warmer. Some regions may become warmer and welcome that, others will not. And warmer conditions will lead to more evaporation and precipitation overall, but individual regions will vary. Sometimes you'll have floods, sometimes you'll have droughts. And a stronger greenhouse effect will warm the oceans and partially melt glaciers and other ice, increasing levels, and ocean water will also expand as it continues to warm. So these are aspects which are likely to happen. Now here's a situation on Mars where there's not enough of this greenhouse effect, and the planet Mars has a very thin atmosphere, and nearly all of it is carbon dioxide. And because of the low atmospheric pressure, with little to no methane or water vapor to reinforce this, Mars has a largely frozen surface with no evidence of life. Now, this is Venus with too much of a greenhouse effect. The atmosphere of Venus is like Mars, is nearly all carbon dioxide, but Venus has about 300 times as much carbon dioxide in its atmosphere as Earth and Mars do, producing a runaway greenhouse effect and the surface temperature hot enough to melt lead. So these are the two kinds of extremes of the greenhouse effect. So while it's reasonable to assume that solar irradiance and sun's energy output changes climate, a variety of studies show that human activity has dramatically caused changes in our climate relatively recently. And this cannot be explained by changes in energy from the sun. So how has this happened? How have we come about to change the entire planet in this runaway manner? And that is the next component of my talk. And it's important to understand both from the way we have come to be, both for the way we have come to be, but also from the theme of this meeting about how the first part showed how we have made sensors to detect all these changes, but how in the second part I shall show how nature has made sensors which we have tried to understand. And in understanding those sensors, we have come to actually control the planet in very interesting and never before done by any other organism manner. So how has the planet shaped us, and how are we shaping the planet's future? Now, the planet is about 4.5 billion years old, and we as humans have been around for 200,000 years in a variety of ways. Humans and our human-like ancestors, some of whom we intermixed with. And this dramatic period from then to now has resulted in us changing the planet to what many geologists call that we are now in what's called the Anthropocene. So when did this Anthropocene, the time when we started changing the planet instead of merely surviving on the planet, start? Now there are two views on this. One is that, as the Anthropocene Working Group suggested, that this started, this Anthropocene period or epoch started on 16 July 1945. So what happened in 16 July 1945? This is the Trinity site in New Mexico, where this is about 16 milliseconds after the proposed start of the Anthropocene. So is this the time when we started changing the planet irreversibly? Or others argue that this period, this epoch started when we started taking to agriculture and we started having livestock, domesticating plants and livestock. That was the beginning of the Anthropocene. Anyway, as that debate goes on, it's valuable for us to ask now, how is it that we came to dominate the planet in this manner? And that required two aspects. One, We evolved, and we, like all organisms on Earth, fought against the environment, or despite changes in the environment, managed to survive. So our initial role was primarily that of survival, like every other organism. But during that route, we accidentally developed certain characteristics: a nervous system, an ability to oppose thumb and forefinger, an ability to speak. And this resulted in us slowly developing properties of cultural evolution, which sped much faster than our evolution by inheriting our DNA, for example. And this cultural evolution allowed us, through language and other mechanisms such as technology, to dominate the planet in a manner which no other animal has. This happened just as this changed the world. Another impact, perhaps of an asteroid 65 million years ago, changed the world in another way when our Earth was dominated by these large beasts. But an asteroid may have changed that, creating a dramatically different atmosphere where these animals couldn't survive, and the much smaller mammals managed to survive and then slowly dominate the entire Earth in a manner as never happened before. So as the mammals developed, and as I told you, because of a variety of evolutionary quirks, humans also started dominating the planet, not just by surviving, but by making tools which allowed them to manipulate the planet. And that's best exemplified by a statement made by Carver McCready, and this is called the McCready explosion. Carver McCready, he designed the Gossamer Albatross, which was a human-powered aircraft which crossed the English Channel. And McCready says that 10,000 years ago, human populations plus our livestock and pets were approximately 0.1% of terrestrial vertebrate biomass. And today they are 98%, right? So of all the vertebrate biomass today, 98% is dominated by humans and our livestock. And this is an awesome change. I've tried to search for the primary source of this data, and they are all cross-referenced. But even if this actual number is not valid, I think the impact is something which is relatively obvious. So McCready says, over billions of years on a unique sphere, that is our planet, chance has painted a thin covering of life, complex, improbable, wonderful, and fragile. And this was our planet. Suddenly, we humans have grown in population, technology, and interestingly, in intelligence. How did that happen? To a position of terrible power. We now wield the paintbrush. So this is the principal challenge we have today, is when we wield the paintbrush on the planet, what do we do to ensure that it's sustainable? And there, at the primary component of that is getting quality data which we can distill, analyze, and use for decision making. And therefore, in every way, what I talked to you about the environment is very important for this. And I'll come to that a little later. Now, how is it that we humans came about to wield this power? And that answer comes from the exploration by humans to try and understand nature, and primarily the exploration by biologists. Biologists ask only three questions. One is, where did we come from? And that's evolution. How are we made? And that's developmental biology. And how do we function? That's physiology. And in asking these three questions, biologists, using the tools available around us, deciphered the meaning of life. And they're still doing that, but they have understood extraordinary aspects of how life came to be. So we know how, from a fertilized egg, a human is made. From a single cell, such a hugely complex organism, how it comes about, the basic principles are known today. And these were all discoveries made substantially in the last 50 years, but over the last 100 years. And principally, we know that there are chemicals which interact at a short range, at a medium range, and a long range, and these control the fates of cells as they divide from a fertilized egg, make them into different parts of the body as we see it, and coordinate the function of all of this. So that's sort of a quick summary of, hundreds of thousands of human years of study. So that's evolution and embryology. Now, what scientists also did was to ask another kind of question, which is, since all life has a common origin at this wall of time equals zero, how is it that different forms of life came about? And that, as I said, is evolution. But it turns out that these different forms are connected by a shared chemistry. And all that shared chemistry has underlying it the common thread of DNA. So DNA is something which connects all life on Earth, and changes in DNA have resulted in both speciation in a variety of species and in changes from generation to generation within a species. The structure of DNA, the DNA was discovered as a genetic material by Avery, MacLeod, and McCarthy at the Rockefeller Institute. But the structure of DNA was elucidated by Watson and Crick using data from Rosalind Franklin and Maurice Wilkins, shown over here. And this told us not only the structure of this molecule, but how it divided and how changes in it could change and give us all this variation in life. Now, I told you how from an embryo, from a fertilized egg, you get an embryo and a human. But one part of the human body fascinates us, which has been so dramatic and so very different from that corresponding part in all other animals that it's allowed us to change the world. And that part is the human brain. The human brain is very different from the brains of all other animals and brains of our other primate relatives, in that it's got a much larger number of neurons, as we now know for sure. And this growth in the number of neurons requires a huge amount of energy. And perhaps the peculiarity of us discovering fire and using that to cook food allowed us to take in our early phases of growth, a high nourishing food, which otherwise our primate relatives would have to be eating 24/7 to be able to manage even a fraction of that. So for some reason, we don't know that yet, our cortex has grown enormously. There's an enormous circuit of parallel computers whose magic we're only now beginning to understand even in a very minor way, whose sensory systems can sense every component of the earth, or many components of the earth, and what's happening, and process that information and take decisions. It's absolutely stunning. And this stunning capability is different from all animals in that we can control what we do to the environment in ways no other animal can. And that's illustrated by this slide from the philosopher Dan Dennett. On the left is a termite hill in Australia. And that is made by a group of termites without a central command, without someone saying build this part better or cut this down or increase that. And on the right is a cathedral in Barcelona, which is built by an architect, a maniac who decided that this structure needs to be done, and there is a central command over there. So nature is capable of extraordinary organization by a mode which we are now beginning to understand, but humans do that in very, very different ways, and they therefore affect our environment in rather dramatic ways. And we understand now, to a great extent, how varieties of animals come about, how they are made, what is their chemistry, and we also have, interestingly, the amazing ability, because of our capabilities like this, to manipulate nature in new ways, such as we've seen technologically. But even in terms of understanding nature, we have now moved from understanding nature's engineering to a capability to engineer nature in its most fundamental aspects, including changing DNA in a manner, changing organisms in a manner through our understanding, which was never before possible. So this capability is absolutely unusual, and it's there because of our brain linking up with our sensory system and our physiology in a manner in which no other animal can. So this has resulted in us being mere survivors on the planet. As I said, that we were, the planet of the apes, and we are moved now because of our technological capabilities to being not the planet of the phones, but the planet of the apps. So this capability has also resulted in a dramatic change in our average IQ over the last 100-ish years, factored in for social, cultural, and economic parameters. That's because cultural evolution has allowed each of us to take on more and more complex and more abstract challenges in a manner never before possible. And this is a link between our brains and the technologies we developed as prosthetics, which are dynamic, and the consequences of that on our ecosystem. Each of our brains, for example, has got two hemispheres which are connected, and they function so rapidly in contact with each other that we think of ourselves as one person. If we had cut that commissure, we would have a split personality. But conversely, if multiple brains could be connected at very high speed, we would be a different individual in a different way. It's a high speed connectivity which can completely transform that. And we have very slow speed connectivity now. And the question is, can we ever reach that kind of connectivity which can even transform our powers of abstraction and control even further? So in this situation, what can we as scientists do? And the situation I'm talking about goes back to the beginning of my talk about climate change and what we have done to the planet. Well-intentioned, but as a consequence of a variety of interferences, here's where we are. We should really start viewing our threats as opportunities. And we should look at from an Indian perspective, the extraordinary strengths of Indian science. Today, we have a situation where the development of the major economies of the world over hundreds of years have come about because, first of all, initially during the first industrial revolution, using the colonies as a source for raw material, then using the rest of the world from the perspective of the West as a place where one could sell one's consumer goods. And then as economies started to grow, have a globally interlinked economy where those who had not pushed forward in science and technology were economically destined to be further and further behind, to a situation now where the emerging economies of the world are trying to lift a large number of their citizens out of poverty. This, a country like India needs to do in a socially inclusive manner, as a democratic country, in a manner where it cannot be primarily as an exporter of consumer goods or of defense products which buffer the economic growth in a big way, where it cannot exploit internally and it cannot and should not exploit internally and externally. So how does one democratically grow an economy in a huge way? And that's a big challenge, but that's a challenge which I feel by collaborating nationally and internationally, Indian science has got a unique opportunity. We have many great centers. The Indian Institute of Technology here in Delhi is an example, the Tata Institute of Fundamental Research, the Indian Institute of Science, and yet these centers of excellence are caught in a chase which I feel they should move away from and grapple with a bigger problem. These institutions are trying to be comparable to the best in the world, and that's a slow, linear process with a small positive slope. So this is going to be tough. It needs to be addressed, but as the world also changes, it's going to be very difficult to be amongst the best in the world by this process alone. So we should see our predicament as being an opportunity. And our predicament, I think, is because we are the wrong color. And I don't mean the wrong pigmentation. India is the wrong color on every map, whether it's the map of tuberculosis, malaria, dengue, Japanese encephalitis, lymphatic filariasis, children under 5 with stunted growth. Our nutrition situation is very bad. Poverty, literacy, corruption, open defecation. So our challenge is changing our color on each of these maps. And that's the focus. If that's the focus of our institutions, then we can excel and be the best in the world, making these predicaments as opportunities for development and applications of technologies which effectively change this landscape. So this is absolutely critical. And one of the errors India has made, which there is, I think, a rapid way out, nevertheless, one of the errors India has made is it has for several decades now addressed its educational and research problems as one of developing capabilities, but it's done that well, and all credit to our great institutions. But it has done that well with our best institutions being a short walk from India. Now, given their core capabilities which have developed, the deep domain expertise which have developed, it's now important to open the door and connect to India. And this is very important because we are not a small country. The name of the country is not Liechtenstein, where we can import everything and we can be a nice banking economy and we can live a nice life in our cottages or castles. The name of the country is India, where there's an extraordinary large demography. And unless our science and technology is driven to address the interesting questions, basic or applied, which are thrown up by our environment, we will end up having solutions which don't necessarily fully solve our complex problems. And that is the challenge. I mean, public transport is important, cars are important, technology is important, but how do we solve it in our context? And that's a very, very big challenge. So we must therefore decide who we are. Are we India or Liechtenstein? If we are India, we should start behaving like India. Now, this principally, all the science and technology and the reach is important. Principally, our challenge is to see what the role of science and technology in this change is. And I think one area which is very important, and this is true not just for India, this is true for countries in Africa, in Latin America, is bringing policy to bear on decision making in a quality way. Does science have a role? I think at this stage in the history of our planet, science is uniquely positioned to be part of the solution in a big way, and countries such as India should step forward and take the lead in developing policy which can be of value both to India and to the planet. So what is our role as scientists? One aspect which we need to push in India is when we sit on committees for decision making, all too often we get a divergent set of views and we postpone that decision making. And here data is very important, and the courage of scientists to take decisions is very important. So again, data on epidemiology, health, disease measured by people like you should come to bear on committees which decide on clinical trials. And these committees should take hard decisions, because if one has to have personalized medicine on scale, if one has to take decisions on health insurance on scale in India, then our committees need to take these decisions and not just import those conclusions which are very valid elsewhere. This is true for clinical trial decisions, what kind of energy we have, what is the role of nuclear versus other sources of energy, renewable sources, our food, our vaccinations, and these challenges should not be seen as too formidable for us. So while I would encourage all of us to work in our laboratories, collaborate nationally and internationally, it's important that the collection, analysis, and distillation of data need to feed back to the highest levels of policy making, in which all of us should participate and take these hard decisions. So in a country where we have several problems, these problems are now being addressed by us, and I think we have made a lot of headway recently in putting together the ability to address that, both over the last few years in squarely pointing out what the challenges are, and over the past few decades in having the capabilities to address them. And therefore, science and its solutions are very important. Science today has a very important role. It traditionally has a minor role, but this time I think it's the fulcrum on which great weights can be lifted. Another metaphor is it's a rudder on a finger on the rudder of a big ship, and Indian science can scale up in a manner which can have global impact. So I'd like to end by saying that the huge, formidable challenges that the planet faces today are a result, identifying those problems are a result of measurement, which our science and technology has done brilliantly. The creation of those problems are a consequence of human effort in a manner which was well intentioned, but moved from survival on this planet to changing it in a manner where now we need another feedback loop which tones down our impact on the planet in a huge way. And it's only by having good data into decision making can we take views on how to reverse this trend. And that's where all of you are really vital. Thank you very much.